Okay, so now we're continuing with question 33 on our semester exam review sheet. So it says, which graph best represents the motion of an object that has no unbalanced force acting on it? So when it says no unbalanced forces acting on it, that means that the forces are balanced. So what does that mean? So if the forces are balanced, that means there's no acceleration. So remember, F net is equal to ma. That's Newton's second law. So no acceleration, that means the acceleration is 0. Now we're going to look at what type of graph do we have. Well, we have, the graphs are all different, so this question's a little trickier. So this is an acceleration versus time graph. This shows a changing acceleration. Okay? So we also know if the acceleration is 0, that could mean that something's moving at a constant speed. So graph number 4 is on a displacement versus time graph. This means the acceleration is 0. On a velocity versus time graph, the slope is acceleration, so this shows a changing acceleration. This is a momentum versus time graph, and this is an acceleration versus time graph. And obviously, this also is not correct. So the answer is D. All right, now let's look at question 34. It says, in the diagram below shows a 2 kilogram block being moved across a frictionless horizontal surface by a 6 Newton horizontal force. What is the magnitude of the acceleration? So I know that F net is equal to ma. That's Newton's second law. So A is equal to F over m. So 6 newtons, and a newton is a kilogram meter per second squared, divided by a meter by mass, which is 2 kilograms. So 6 divided by 2 is 3. And when we carry the units through and cancel them, it's a foolproof way to check our work. So this kilogram cancels with that, and I end up with meters per second squared, which is the correct unit. Oh, we're not solving for the acceleration. Oh, yeah, we are. So it comes out to be 3 meters per second squared, which is choice C. So this is C. This was D. All right. Number 35, it says a series of unbalanced forces was applied to each of the 2 blocks A and B. The graphs below show the relationship between the unbalanced force and the acceleration compared to mass A. So first of all, if we look at this, we know F is equal to ma. So m is equal to F over A, which happens to be the slope. So since the slope is represented by the mass, it says which one is greater. Now, in this one, it has the mass. So you can see that this slope is greater than that one. Okay? But I don't know the actual number. So I'll just find the slope here. So I'm just going to pick these 2 points. So remember, slope is delta y over delta x, which is y2 minus y1 over x2 minus x1. So for this graph, I'm going to say 3 minus 0 over 3 minus 0. So 3 over 3 is 1. And then for this one, I'll pick this point and this point. So I'll say 4 minus 0 over 2 minus 0, and 4 divided by 2 is 2. So this one is 2 kilograms, and this is 1 kilogram, so it's going to be twice as great. B. All right, now let's go to number 36. So it says 2 forces are applied to a 2 kilogram block on a frictionless horizontal surface as shown in the diagram. What's the acceleration? So I have, remember, force is a vector quantity. It has both magnitude and direction. So I have a force going to the right and a force going to the left. So the correct way to think about this problem is, I know that the summation of F net is equal to ma. So the net force I have, I'm going to use my standard Cartesian sign convention. Up and to the right is positive. So I have 8 newtons, which I'm going to call that positive, minus 2 newtons is equal to ma. So now I'll rearrange that, and I'll say 6 newtons divided by 2 kilograms is equal to 3 meters per second to the right, because I'm calling to the right positive. So that's going to be choice C. Remember, this is F net is equal to MA, so I rearranged it that A is F net over M. All right, now we're going to move on to the next page. So we're going to look at 37. And remember, when you're actually taking the test, what you want to do is you want to have your scrap paper like this side by side when they're ones that you have to do calculations with. Okay, so you don't write on the test and you put your paper right here, right next to it. All right, number 37 says an unbalanced force, so I know F is equal to 10 newtons, causes an object to accelerate, so A is 2.0 meters per second squared. What is the mass? So F is equal to MA, so M is equal to F over A. So I have 10 kilogram meter per second squared divided by 2 meters per second squared. So this meters per squared cancels with that, so I end up with kilograms, and 10 divided by 2 is 5. So the answer to number 37 is B, 5 kilograms. Number 38, an unbalanced force of 10 newtons acts on a 20 kilogram mass. Remember, I'm chunking. I read, I write. I read, I write. For 5 seconds. What is the acceleration? Well, I know that F is equal to MA, correct? So I want to find the acceleration. So A is equal to F over M. So it's going to be 10 newtons, so 10 kilogram meter per second squared divided by the mass, which is 20 kilograms. So this kilogram cancels with that, so 10 divided by 20 is 0.5 meters per second squared. So the time has nothing to do with the question. So sometimes they give you extra information that you don't need, but you have to figure out what do I need and what don't I need. And that's why writing down your given and find helps. So the answer to number 38 is A. All right, number 39. An elevator containing a man weighing 800 newtons is rising at a constant speed. So if we look at a free body diagram, and this is chapter 4, here's my weight, F of G. Here's my normal force acting up, okay, which is also the reading on the scale. The force exerted by the man on the floor in the elevator is, so they want to know what's the normal force, okay? Well, the key here is constant speed. If you remember when we did our elevator lab, if it's moving at a constant speed, that means the acceleration is 0, so the forces are balanced. Which means it's just going to be 800 newtons. All right, number 40. It says a ball having a mass m is struck by a bat having a mass 9m. Compared to the magnitude of the force exerted by the bat on the ball, the magnitude of the force exerted by the ball on the bat is, and they're going to be the same because this is Newton's third law. Okay, this is Newton's third law. All right, number 41. Which diagram represents a box in equilibrium? So equilibrium means that the forces are balanced. So I have to look. So I'm going to look at all the choices, and the ones where the forces are balanced in both the x and the y direction is going to be choice C. All right, so now let's go and look at 42. So 42 says the diagram below represents two forces acting concurrently at point P. So first of all, the concurrent means acting at the same point at the same time. It says which diagram represents the resultant. So remember, when I add scalar things, I can add them algebraically. But when I add vectors, instead of a sum, I get a resultant. And vectors are added head to tail. These are tail to tail. So in order to add them head to tail, I can move, I'll just leave my 10 Newton one the same, and from the head of this vector, I do the tail of the other. And then from where I start to where I end up, this is my resultant. Okay? So vectors are added head to tail, and we're not calculating it. They just want to see the which diagram represents the resultant. So that's going to be choice D. If I was going to calculate that, I would have to use the Pythagorean theorem because it's a right triangle. All right, let's look at number 49. A man walks 40 meters north, 70 meters east, and then 40 meters south. What's a displacement? So displacement is a vector quantity. So it's from where I start to where I end up. So you can just pick a point. So let's say to show it, I start here. I go 40 north. Then I go 70 east. And then, remember, from the head of this vector, I do the tail of the other. From the head of this vector, I do the tail of the other. So this is where I started, and this is where I end up. So where I start is the tail, and where I end up is the head. So I see that I go 70 meters, but from here to here, I see it's, this is where I started, and this is where I end up. So my answer is 70 meters east. Because the direction is important. So the tail is at the start and the head is at the end, where I end up. All right, let's look at number 44. So number 44 says a mass is moved 9 meters north and 12 meters east. What's the displacement? So this is where I start. So I go 9 north. From the head of this vector, I do the tail of the other, 12 east. So displacement is a vector quantity, has both magnitude and direction. This is where I start, this is where I end up. So this is my tail, this is where I start, and then my head is where I end up. So I have a right triangle, I have two sides, so I can find it using the Pythagorean theorem. So 9 squared plus 12 squared. And then I take the square root, and that ends up being 15, which is choice B. Number 45, a student walks. So again, I might want to draw a picture. I don't really have room here, so maybe I'll do it on a piece of paper. A student walks 3 blocks south, so this is where I start. So the student goes 3 blocks south, 4 blocks west, 3 blocks north. What is the displacement? So displacement is from where I start to where I end. So it's going to be like this. So I see that it's 4, but you see how it's pointing to the left? Okay, that's why understanding vectors, understanding the direction is extremely important. So the answer would be 4 blocks west, because according to my sign convention, remember, we're using standard directions, north, south, east, and west. So going that way is west. Okay? So the answer here is D. All right, number 46. It says the resultant of 2 forces acting on the same point at the same time will be the greatest when the angle between them is, well, it might help us to conceptualize this as a picture. Okay? So I want it to be the greatest. So if I had 2 vectors and the angle between them is 0, when I add them head to tail, this is my resultant. When they're going in opposite directions, they could cancel each other out. Okay? So when the angle between them is 0, I'm going to have the greatest angle. So again, if I have this plus this, that's my resultant, head to tail, right? And now it says the resultant of 2 forces a minimum when the angle between them is 180, because if I had this plus this, I would end up with 0, right? So this one is going to be 180. And this all has to do with knowing that vectors are added head to tail, not tail to tail. Okay? All right, so let's go on to number 48. So number 48, it says, in the diagram below, a box is at rest on an incline. Which vector represents the direction of the normal force? So acting straight down is the weight, and the normal force always acts perpendicular to the surfaces in contact. Okay? So the answer here is going to be C, because I need to know that the normal force is always perpendicular to the surfaces in contact. So that's C. Number 49, 2 students are pushing a car. What should be the angle of each student's arm with respect to the flat ground to maximize the horizontal component of the force? So again, if I look at a picture, if I pull this way, this is F. If I pull at an angle, what's going to happen is my horizontal component of that, which is the person is going horizontal, is going to be F cosine theta. So as I increase this, I see my horizontal component is going to decrease. So just pulling it straight is going to give me the greatest force. All right, 50. The diagram below represents a car resting on a hill. Which vector represents the weight? So we don't know the weight always acts straight down. So that's B. Number 51. A 75-kilogram bicyclist coasts down a hill at a constant speed. So we know constant speed. What is kinetic energy? Oh, so now we're up to Chapter 5, work, energy, and power. That was the end of Chapter 4. So now we're up to Chapter 5. Well, I know that kinetic energy is equal to 1/2 mv squared. So it's going to be 1/2 times 75 kilograms times 12 meters per second squared. So when I do all that on my calculator, the kinetic energy comes out to be 5,400 joules. And then, obviously, here they have it in correct significant figures, which is 2. So it would be 5.4 times 10 to the 3 joules. All right, let's look at number 52. Number 52 says, which graph best represents the relationship between the kinetic energy and the velocity of an object traveling in a straight line? Well, first of all, let's look at my equation. Kinetic energy is 1/2 mv squared. The velocity is squared. Okay? The velocity is squared. So as this increases, this is going to increase like a squared function, right? So that is choice D. It's not linear because they're not directly proportional. This is proportional to the square of the velocity. All right, number 53. It says, if the velocity of a moving object is doubled, the kinetic energy, well, again, the first thing you should do is think of the equation. So for number 53, kinetic energy is 1/2 mv squared. So now it says the velocity is doubled. So now kinetic energy is 1/2 m2v squared. So when I square the 2, I also have to square the v. So this comes out to be 1/2 m4v squared. So now when I look at the difference between this and this one is 4 times as much, or it's quadrupled, which is choice D. All right, number 54. It says if the kinetic energy of a 10 kilogram, that's the mass object, this is the kinetic energy, what's the velocity? So I'm going to start off with the equation. Kinetic energy is 1/2 mv squared. And I want to solve for the velocity. So I'm not going to plug in. That's how I make mistakes. I'm going to rearrange the equation to solve for the unknown in terms of the known. So I'm going to multiply both sides by 2. Then I'll divide both sides by m. And then I'm going to take the square root of both sides. So the square root of 2ke over m is equal to v. Now I'm going to substitute in my values. So 2 times 2,000 joules. And I know a joule is a Newton times a meter. And a Newton is a kilogram meter per second squared times a meter divided by 10 kilograms. So this cancels with that. So underneath the radical, I'm actually going to have, besides my number, I'm going to have meter squared over second squared. So when I take a square root of the number, I also take the square root of the unit, and I get meters per second, which is the correct unit for velocity. So that's why we carry our units through and cancel to check our work. So this one comes out to be 20 meters per second, which is choice B. All right, now we're going to go on to number 59. Oh no, 55. That was 54, so now we're up to 55. So 55, it says 3 people of equal mass climb a mountain using paths A, B, and C, as shown in the diagram. Along which path does a person gain the greatest amount of potential energy from start to finish? So we know that potential energy, which gravitational potential energy, is mgh. Okay? So mgh, here's where I start, and this is just the vertical height like this. So because they all go from here to here, the answer is they're all going to be the same. So this is choice D. All right, number 56. As an object is raised above the Earth's surface, the gravitational potential energy, that's going to increase because we just said potential energy, gravitational potential energy is mgh. So as h increases, this is going to increase. All right, number 57. It says a 5 kilogram mass, so we're going to chunk. This is the mass. Is raised vertically 2 meters, that's h, it's gaining gravitational potential energy. So we're just going to do mgh. So it's going to be 5 kilograms times, and I'll just approximate gravity is 10 meters per second squared times 2. So 10 times 2 is 20, times 5 is 100. All right, let's look at number 58. So 58 is a little bit more complicated. It said the diagram below represents 155 Newton box. So that's my weight, F of G. And remember, F of G is equal to mg. Applied a force causes the box to slide from point A to B. What is the total amount of gravitational potential energy gained? So remember, I'm going from the ground to up here. So I know gravitational potential energy is mgh. Well, I already know mg, which is fg, which they told me is 155 newtons, times the height from here to here is 1.80. So 155 times 1.8 comes out to be 279, and a Newton times a meter is a joule. So that's going to be choice B. All right, let's go back to the next column. So number 59, the work done in accelerating an object along a frictionless horizontal surface is equal to the object's change in. So this is the work is equal to the change in energy. So this is the work energy theorem. So now because this is accelerating and it's moving, this is going to be the kinetic energy. So work is equal to the change in kinetic energy. All right, number 60. It says in the diagram below shows three positions, A, B, and C, in the swing of a pendulum released from rest. So remember, whenever we measure stuff, we have to have a frame of reference, which is going to be the ground. So we're basically going from like here to here. Which statement about the swinging pendulum is true? So before I read the choices, at this point, if it's at rest here, because at A it's at rest, that means this is all gravitational potential energy. So at this point, the potential energy is equal to a max, and because it's not moving, the kinetic energy is a min, which is actually 0. As it starts to fall, I'm going to lose potential energy, gravitational potential energy, because it's getting closer to the ground. But whatever I lose in potential, I gain in kinetic because the total amount of energy is the same. At the bottom, that's my frame of reference, the ground. So there, my gravitational potential energy is 0, and that's where my kinetic energy is going to be a maximum. But the total energy remains the same. So if I read all the choices, the correct choice is going to be D, the potential energy at A equals the kinetic at B. All right, 61. It says, which object has the greatest momentum? So this is chapter 6. So now we're up to chapter 6. So momentum is mass times velocity. So P, that's the physics we're doing here. Remember, on my review sheet, next to each question, I want to say to myself, what physics concept am I using to answer this question? So P is equal to mv. So I just multiply all these out. So 12 times 1 is 12, 10, 27, 16. So this one is the greatest, and that's my answer. C. All right, number 62. The product of an object's mass and velocity, mv, that's just the definition of momentum, because I know P is equal to mv. Number 63. An object traveling at 4 meters per second has a momentum of 16 meters per second. An object traveling at 4 meters per second has momentum of 16 meters per second. What is the mass of the object? So this is just a definition of momentum. So first I would write my equation, P is equal to mv, and I want to solve for the mass. So m is equal to P over v. So it's 16 kilogram meters per second divided by 4 meters per second. So this meters per second in the numerator cancels with the one in the denominator, and I end up with kilograms, which is the correct unit for mass. That's why I carry my units through and cancel them. And 16 divided by 4 is 4. So the answer there is D, 4 kilograms. So we're on chapter 6. All right, now we're going to do question 64. It says an airbag is used to safely decrease the momentum of a driver in a car accident. The airbag reduces the magnitude of the force acting on the driver by, so first of all, remember the change in momentum, delta P is m delta V, but it's also equal to Ft. So it's going to increase the length of time the force acts on the driver because delta P is equal to Ft. Number 65, a 0.14 kilogram baseball, so that's the mass, initially moving at 15 meters per second, that's the initial velocity, is brought to rest, so that's the final velocity, in 0.04 seconds by a baseball glove. What's the magnitude of the force? So this is the impulse momentum theorem. And this one I have to calculate, so I'm going to take a nice piece of paper here and put it next to here. So I know that Ft is equal to m delta V. So F is equal to m delta V over T. So F is equal to m Vf minus Vi over T. So F is equal to 0.149 kilograms times 0 minus 15 meters per second divided by 0.040 seconds. Now, first of all, a kilogram meter per second divided by a second is a kilogram meter. Oops, you can't, I'm off the screen. That's a kilogram meter per second squared, which is a Newton. So that my unit works out. On my calculator, I get 55.9, which is 56 newtons, and correct two significant figures. So that's going to be answer D. All right, number 66. A 20 kilogram mass moving at a speed, so we have the mass is 20 kilograms, moving at a speed of 3 meters per second, is stopped, so this is the initial velocity and this is the final velocity, by a constant force of 15 newtons. How much time? So this is exactly the same as the last one, except now we're solving for the time. Okay? So you're going to say Ft is equal to m delta v. So T is equal to m delta v over F. So it's m Vf minus Vi over F. And when we do all that, you can do the math yourself. We end up getting 4 seconds. So you just have to substitute in the values. All right, number 67. As shown in the diagrams below, a lump of clay travels horizontally to the right toward a block at rest on the frictionless surface. Upon collision, the clay and the block stick together and move to the right. Compared to the total momentum of the clay and the block before collision, the momentum of the clay block system after collision is the same, because we have conservation of momentum. So that's going to be choice C. All right, number 68. The total momentum of a system that consists of a moving rocket and its exhaust will remain the same because of, again, same thing, conservation of momentum. All right, let's look at number 69. So number 69 says a rocket engine acquires motion by ejecting hot gases in the opposite direction. This is an example of, again, conservation of momentum. Number 70, a student drops 2 eggs of equal mass simultaneously from the same height. Egg A lands on the tile floor and breaks. Egg B lands intact without bouncing on a foam pad lying on the floor. Compared to the magnitude of the impulse on pole B, well, the impulse is equal to the change in momentum, which is m delta v. And I wrote this in the wrong place. That goes down here. So, again, this is going to be the same. All right. And that's the end of chapter 6. So, what I'm going to do is, let's see, we only have 10 more questions. I guess we can do 10, right? All right. So, number 71. It says an object is traveling with the velocity, so that's v, of 6 meters per second in a circular path with a radius of 9. What's the centripetal acceleration? So I know that centripetal acceleration is equal to v squared over r. So centripetal acceleration is equal to 6 meters per second squared over r, which is 9 meters. So 36 divided by 9 is 4. I can do that in my head. And again, we want to carry our units through and cancel them. So I have a meter squared over a second squared divided by a meter. So I end up with meter per second squared, which is the correct unit for acceleration. So the answer to number 72 was D. I already wrote that. All right, that was 71. 72, an object traveling in a circular path of radius 5 meters at a uniform speed of 10 meters, what is the magnitude of the centripetal acceleration? This is the exact same equation. So centripetal acceleration is v squared over r. So it's going to be 10 meters per second squared over 5. So 100 divided by 5 is 20, which is choice D. And again, we want to carry our units through. Oh, why didn't someone tell me it froze? Oh, maybe it didn't freeze. Let me see. Whoops. It didn't freeze. It's still going. All right, just my monitor froze. Sorry about that. All right, so we're almost there. Number 73. In the diagram below, a cart travels clockwise at a constant speed in a horizontal circle. At the position shown in the diagram, which arrow indicates the direction of the centripetal acceleration? So we know centripetal acceleration always acts towards the center of the circle. So we know that one is just A. So that's super easy. Hopefully that didn't freeze when I think we might not see that part where my screen froze, you know what I'm saying? But that's okay. All right, 74. So a stone on the end of a string is whirled clockwise at a constant speed. Which pair of arrows represent the direction? So we know that here's where the stone is here. So it's going this way, and the velocity is always tangent to the curve at that point and that point only. So this is my velocity. It's going down because it's going clockwise. If it went counterclockwise, it would be going up. And then we know the acceleration always acts towards the center. So the answer there is D. All right, so now for 75, it says base your answers for 75 through 77 on the diagram below. And it shows a student swinging a 0.1 kilogram, so this is the mass, ball, and this is the radius of the string at a constant speed of 10 meters per second. So again, as we read, we want to chunk. We want to read, we want to write. So it says, if the magnitude of the force applied by the student's hand is increased, the magnitude of the acceleration. So I need to think about the equation. So F of C is MAC. So these are directly proportional. This is like the lab that we did in class. So if this is going to increase, this is also going to increase. And then when you're not sure about the relationship between variables, you write down the equation. Is it directly proportional? Is it inversely proportional? Is it proportional to the square? All right, number 76. It says the magnitude of the centripetal force required to keep in this path. So now I actually have to calculate that centripetal force. So we know centripetal force is equal to mv squared over r. So the centripetal force is equal to 0.10 kilograms times 10 meters per second squared over r, which is 0.50 meters. So when I do the math on my calculator, it comes out to be 20 newtons, which is choice C. All right, number 77. So number 77 says, which is the best description of the force keeping the ball? So we know that because centripetal force is equal to MAC, whatever direction the centripetal acceleration is the same direction of the force, which is going to go towards the center. So it's going to be choice A, perpendicular to the circle and directed towards the center. So that's going to be A. Number 78. The path of a satellite orbiting the Earth is best described as elliptical. And that's Kepler's first law. So we need to know that this is Kepler's first law. Question 79. The shapes of the paths of the planet around the sun are ellipses with the sun at one focus. Okay, so remember it looks like this. And again, that's Kepler's first law again. So that's choice D. And we only have one question left. So this one talks about Halley's Comet, and it says, base your answer, so at which position is the speed the greatest? So here, when it's farther away, I'm going to have more potential energy and less kinetic energy. And here I'm going to have more kinetic energy and less potential energy. So the answer is going to be D, because here I have more kinetic energy, and kinetic energy is 1/2 mv squared. So it's going to be going faster here, and it's going to be going slower here. So again, since kinetic energy is 1/2 mv squared, when it has the greatest kinetic energy, it will have the greatest speed. And that's it.